Hi everyone. The paper I have prepared is ALC, additive rounding and clipping, considering gradient distribution for the convolutional neural network training. We start the presentation. The contents I have prepared are as follows. In the introduction and background section, I will explain the motivation and contributions of the proposed method as well as the background knowledge. Next, I will introduce the proposed method and explain the experimental results. Finally, I will present the conclusion. Convolutional neural network have made significant advancement in various vision tasks, such as classification, detection, and segmentation, achieving high accuracy. However, the increasing complexity of CNS requires significant computational power. This presents a major challenge when deploying these complex CNN models on devices with limited hardware resources, such as embedded and edge devices. To solve this problem, various compression methods have been studied, with quantization gaining attention for its ability to significantly reduce hardware resource and power consumption. While quantization training can achieve high accuracy, it has the problem of high training cost. Moreover, quantizing the gradients which directly affect the training is even more challenging. Previous studies have used stochastic rounding for stable training. However, generating random numbers incurs high hardware resource requirements and latency. Additionally, the converted gradient distribution during training makes the applying of quantization difficult. To address this issue, we propose a quantization framework that considers the gradient distribution. To reduce hardware resource and latency, we employ deterministic rounding. Furthermore, to handle the converting gradient distribution during training, we explore clipping values based on Z-score. Our proposed method has achieved high accuracy in various vision tasks and ensure high flexibility. We have also demonstrated the excellence of our method through RTL and CPU resource measurement. Next is the background. Quantization is a compression method that performs CNN computation with lower bit widths instead of the standard 32-bit floating point operation. Quantization can be broadly classified into three categories. First, post-training quantization quantizes the model during inference and does not require retraining. Quantization training quantizes the model during training, recovering accuracy through fake simulation. Mixed precision quantization allocate different bit width to each layer. Through quantization, we can effectively reduce the energy cost and inference time incurred by convolution operation, which account for most of the computation. We explain the type of rounding operations which are significant to quantization. Deterministic rounding, which projects value to the nearest discrete level, is commonly used in most quantization research. Stochastic rounding is a method that rounds value using random numbers, while deterministic rounding cannot project value to the right quantization point. Stochastic rounding can project value according to probability. Therefore, it allows unbiased quantization and is widely used in gradient quantization research. Next are the challenges of gradient quantization. The quantizer is a step function, making it non-differentiable. This implies that parameter updates are not possible. Therefore, most prior studies use a straight-through estimator method that bypass the gradient of the previous layer. Gradient is important value for updating network parameters. Incorrect gradient quantization causes network divergence. Additionally, Quantization alters the magnitude and direction in the loss space, preventing the model convergence toward the minimum point in the loss space. Next is the proposed method. Our goal is to propose a quantization framework to reduce the latency and power consumption of CNN backpropagation. To consider the changing gradient distribution during training, we propose a cliffing value exploration method. We calculate z-score to identify outlier in the distribution. Traditionally, in statistic values with a z-score greater than 3 are considered outliers. Therefore, if the maximum z-score value is less than 3, we apply the min-max clipping method. If the z-score value is greater than or equal to 3, we use the top end percent of z-score indices as the clipping value. To address the high hardware resource requirements and latency caused by stochastic rounding, we apply deterministic rounding. However, conventional deterministic rounding can introduce by doing quantization, potentially causing the network to diverge. Therefore, we apply different type of deterministic rounding based on the distribution space. The distribution discriminator uses a log likelihood function to discriminate between Gaussian and Laplace distribution. For Gaussian distribution, we apply nearest rounding, and for Laplace distribution, we apply rounding toward zero. Rounding toward zero, round value based on their signs. For positive values between 0 and 1 are projected to 0. However, this can lead to large quantization error for extreme value close to 1, such as 0.9. To overcome this issue, we empirically determine an appropriate threshold to mitigate the accuracy degradation caused by extreme quantization. Next context is the experimental result. We use hyperparameters in the cliffing value exploration method and rounding method. If the rounding threshold is 0.5, it will cause network divergence due to performing the same operation as nearest rounding. On the other hand, if the rounding threshold is 1, there will be accuracy loss due to extreme quantization errors. We found that a rounding threshold of 0.8 and a clipping threshold of 10% yield the best accuracy. If the clipping threshold is at a higher value, like 20%, it can decrease accuracy due to the loss of the significant amount of information from excessive clipping. We perform experiments on detection and segmentation takes SLS classification tasks. AR and ZC refer to additive rounding and z-score-based clipping value exploration, respectively. In the ResNet 18 experiment, we achieved a higher accuracy with only a 0.65% drop compared to the baseline, outperforming most other methods. Although our accuracy is 0.02% lower than UI8, ARC used deterministic rounding, resulting in lower hardware resource requirements and latency. Furthermore, when evaluate on the Pascal-Rios dataset using ULECT and UL5, we achieved the high accuracy. Finally, the conclusion. Our proposed method introduces a gradient quantization framework to reduce hardware resource and latency in CNB propagation. To reduce hardware resource, we employ adaptive deterministic rounding based on distribution shape. Additionally, we proposed a Z-score-based clipping value exploration technique that considers outlier in the distribution. Our method achieve high accuracy in various vision tasks. Through our method, we expect to accelerate the common duration of deep learning. Thank you.